In this video, I'm going to tell you how SHSAM works. For the rest of this video, I'm going to kind of hash through how some of the testing was done at the University of Minnesota, and this is the data that SHSAM is based on. So it's important to know how this testing was completed to know how reliable SHSAM is. So researchers started off with 3 different particle sizes, and a lot of these devices only capture heavy sand particles. They'll capture some of the heavier silts, maybe get into the silts, but in general they're only capturing the heavy stuff, unless they're using a filter or they're exceptionally large. They're most likely going to capture particles kind of in this sandy range. So researchers took this range, and what they did is they would take sediment and they would sieve it down into these 3 particle sizes. So you're looking at roughly 450 microns, 335 microns, and 110 microns. So you kind of have a big, medium, and small particle size that these researchers were working with. What they do then is they load equal amounts of these particle sizes, small, medium, and large, into a stormwater BMP, doesn't matter which one, at a constant flow rate. And then they'd feed in the sediment at a constant flow rate, at a constant rate too. So you turn on the water, you fill up the device with water, get water flowing through it, and this is clean water, and then you feed in the sediment at a constant flow rate or a constant feed rate over a set duration, let's say that a couple of hours. Let this experiment run, you're filling the device with sediment, you finish feeding it with sediment, you turn off the water, they would drain the water down, they'd pull all of that sediment that was captured from the BMP, because not all of the sediment was captured, some of it blew through and other particles settled. You take out all of the sediment that was captured, dry it, weigh it, and then sieve it into its original 3 particle sizes, small, medium, and large. So you knew that you had fed in 11 pounds of each of the originally fed in 11 pounds of each size. Well, now you would be able to say, okay, for example here, we captured 9 pounds of the big particle size, and then let's say 4 pounds of the medium size, and maybe 1 pound for the small size. And with that, you can get a removal percentage. So at that flow rate, we were able to capture the removal efficiency for the big particle size was, let's say, 80, medium size was 40%, and then the small size would say something like 10%. So you get a data point for each of those particle sizes. Then what you can do is, for that BMP or several BMPs, you can put it into a chart like this, where on the x-axis you have flow rate, and on the y-axis you have removal efficiency. That was the percentage of the sediment that was captured. So let me pull up a highlighter here. Okay, so for this chart we have 2 different stormwater BMPs. We have a sump manhole. Both of these are sump manholes, but one is 6 foot in diameter and 3 feet deep, and the other one is 6 foot diameter and 6 feet deep. So this is the bigger one, this is the smaller one. This one's twice as deep as this one. So let's look at the smaller one first. Now we have a data point for each of the particle sizes, and then we have data points at different flow rates. So let's look at the small particle size, it's these blue diamonds. So at a low flow rate, you're going to capture about 30% of this particle. Well, and then as you increase flow rate, you're going to capture less and less. That kind of makes sense. If you're blowing water through this structure, it's going to have less time, less hydraulic residence time for that sediment to settle out. Well, and then let's look at the medium particle size. We're up in here. Similarly, as you increase flow rate, you see less and less capture. But in general, this device was able to capture more of the medium particle size than of the small. And that makes sense. And then for the final particle size, we have slightly more, a little bit of variability in the data here, but in general we're seeing higher capture rate with the highest or the heaviest particles. Makes sense. Well, now let's look at the bigger, let me clear off this. Okay, now let's look at the bigger structure. So you can do the same thing here, small particle size, medium, large particle size. So in general, you're seeing the same trends. You're seeing a decreased capture with increased flow rate, and you see the most capture of the big particles than of the small particle sizes. Well, as an engineer, it's really hard. I mean, you can decipher a chart like this, but nobody wants to decipher a chart like this and then try to apply it to their site, because with a storm you never get a constant flow rate. You're getting a variable flow rate, and the particles are kind of flowing in. You don't necessarily always have 545, 335 micron or 110 micron particles flowing in. Your sediment distribution is going to be different than that. So that's where the researchers, let me get rid of this. Okay, the researchers wanted to solve this problem, so they came up with two-dimensionless numbers, and these numbers are from the wastewater industry, and you can look up the documentation on these. This is the Pecklet number, and the second one is the Froude number. Look at the documentation, get more detail on these if you're curious. But basically, the engineers are taking these two dimensionless numbers, and these dimensionless numbers carry all of the main variables that determine whether or not a device will capture sediment. So here are the main variables. We have, this one is sediment settling velocity. Now these two, H and D, these are the dimensions of the device. This is the height and the depth. This is the diameter. The D is the diameter, and this is the depth of the structure, the H. And Q is the flow rate. And then with the Froude number, we have the velocity of the water entering the device, gravitational constant, and the diameter of the structure again. So these two numbers come together, and you're able to kind of collapse all these curves on each other. So what it kind of reminds me of is Captain Planet. I don't know if any of you guys watched that, but I watched that show as a kid. And the idea was there are these 5 teenagers or whatever, and they each have these rings, and each ring represents a different element. So we have earth, wind, water, fire, and heart. Nobody wants the heart ring, but he had it. But all of these different elements combined, when these kids kind of shoot their rings together, Captain Planet pops out. So this is a lot like Stormwater and the Pecklet number and the Froude number, because the Pecklet and the Froude number combined, they take all of these main variables that determine how much sediment your device will capture. So you have temperature, BMP dimensions, you have inlet pipe velocity, particle size, flow rate. All of these different variables are combined to a dimensionless number that's PE over FRJ squared, Pecklet over Froude number. So we were looking at this chart before. If you do this for all sorts of different structure sizes and flow rates and particle sizes, you just keep on repeating this same kind of testing, and then you use the dimensionless numbers, you get all that data to collapse into a nice S-curve. So let's kind of break down what this S-curve means. So over at 0 here, this means that you're capturing 0 sediment. Your removal efficiency, your capture efficiency is 0. So this would be at very high flow rates with very small devices with really small particles like flour. And as you work higher and higher up into here, you get 100% capture. So this would be really, really big structures with very low flow rates, and your sediment particles are like boulders, just huge particle sizes. And this S-curve represents everything in between. Well, let's throw this on. Okay, you can make a curve like this for each device. So in this one, we're looking at the curve with a SAFL baffle installed into a sump manhole and without. And you could do this for all the different devices that are on the market that were tested at the University of Minnesota. Basically, SHSAM has one of these curves for each of the devices. And what SHSAM does is it takes all the watershed information that you enter, curve number, percent impervious, area of your watershed, slope, hydraulic length. And then what it does is it takes the precipitation data that you inputted usually over 10 to 15 years of time period in 15-minute intervals, and then it takes the sediment concentration and distribution that you set. It takes all of this information, the precip, the watershed characteristics, and the sediment, and then it flows it, simulates sending it through your BMP in 15-minute intervals using those dimensionless curves that we talked about earlier. And it'll do this every 15 minutes. So, let's say during a storm you're starting to capture sediment, you're capturing more, and throughout the year, over the period of years, SHSAM is calculating how much sediment you're actually capturing.